Welcome to a lecture that is an application of a general curvilinear motion. They will be discussing the flight of a particle in a projectile motion. So, when an object has an initial velocity, VA, as shown in this figure, it would have its flight according to its path of motion. Now, the path of motion that will be created because of this initial velocity is actually parabolic. So let's discuss the geometric aspects of this projectile motion, also including the velocity of the particle. So the free flight of motion of projectile is often studied in terms of its rectangular coordinates. So it's also a curvilinear motion, and like what we do in curvilinear motion, to easily understand or to identify the geometric aspects of motion, we resolve the velocities into its rectangular coordinates such that this initial velocity could be resolved into its x and y component. For example, at point B, we analyze the velocity of a particle into its rectangular components. We have VBX and VBY. So VBX represents the velocity along x, and VBY represents the velocity along y. Now, without the factor of air resistance, wind velocity, and rotation of the Earth, the x component velocity is actually equal throughout the flight of the projectile. So the x component velocity at point A of a particle is also equal to the x component of the velocity of a particle at point B. We can say that VBX is equals to VAX, and that is termed as simply Vx. So most of the time, when we are talking about the horizontal component of velocity of a particle in a projectile motion, we represent all the values of x component velocity simply as Vx. In some calculations, it indicates the point where the particle is. For example, if you're talking about the velocity point B and the x component velocity is represented as Vbx. Now, without the factor of air resistance, wind velocity, and rotation of the Earth, the y component of an object in projectile motion is actually variable because of the effect of acceleration due to gravity. In this case, the y component velocity at point A is not equal to the y component velocity at point B. Again, it is because of the influence of acceleration due to gravity. Now, the position of the particle is now at B, defined by its coordinate xb and yb. Eventually, as the particle traverses the flight of this projectile, initially from a positive velocity, positive y component velocity, it will be decreased because of the negative acceleration due to gravity and will eventually reach equal to 0. So from a value of a positive, will eventually lessen and lessen until it reaches the value equal to 0. But the y component at this point where there is 0 y velocity still remains at Vcx. So the x component velocity at A, at B, and C are all equal. This is based on our previous discussion. So this is the highest point of the projectile because a positive y component velocity gradually decreases its magnitude until it reaches 0, and then eventually, because of a negative acceleration, it will gain a negative velocity downward, and it starts to move downward. So this becomes now the point where the particle reaches the maximum height. So again, it starts to gain a downward velocity, and it will no longer move upward, but rather its position about y-axis will start to go downward. So let's continue the path of motion of the object. So as it moves from point C to point D, you can see VDX will still remain equal to the x components of A, B, and C. But this time, the y component velocity of this particle at point D now has a negative magnitude. So starting from the positive magnitude and decreasing its value until it reaches zero, it will now start to gain a downward or a negative velocity. So if points A and E are on the same elevation, the time it takes from point A to travel point C is also the time it takes to travel from point C to point E. So the time from A to C is also equal to the time from point C to E. That's one point to note. So we have this equation. So in that case, it also applies the time of travel from B to C and C to D, provided that points B and D are at the same elevation. On terms of y component velocity, if A and E are on the same elevation, the y component velocities are equal in terms of magnitude, but opposite in terms of their direction. So at point A, we have a positive velocity, and at point E, we have a negative velocity. But they have equal amount of magnitude. X component, again, is the same. Again, throughout the flight, the x component velocities are constant or have the same value. So the same principle for points B and D. So if they are on the same level or the same elevation, the y component velocities are equal in terms of magnitude, but opposite in terms of direction. And in all cases, again, the x component of velocity at point B and point D are equal. So let us recall the horizontal motion equation. This is a velocity is a function of time. So the velocity is influenced by acceleration. And this is the equation discussed in our previous lectures, where v sub 0 is the initial velocity of the particle. Since the x component is constant and is not influenced by the acceleration, take note that the acceleration is a vector quantity that is acting vertically downward. So it has no x component. If this acceleration vector has no x component, definitely it won't affect the velocity of the particle in terms of its x component, or it will not affect the x component velocity at all, because its acceleration is influencing the velocity only on the y-axis. So we have the acceleration along x-axis termed as 0, which means that the final velocity and the initial velocity when analyzing particle in projectile is constant throughout the path. If we want to solve for the velocity along x-axis, we can just simply solve it using the definition of velocity, or average velocity, which is the change in position over the time observed. For the vertical motion, it is noted that it's not constant throughout the flight, but it is influenced by the acceleration due to gravity. And using the same equation of the velocity as a function of time, where v sub 0 is the initial velocity, the y component acceleration of the particle is due to gravity, and that we can simply replace AC with a negative g. In some books, you will see this equation, but this equation is still equally correct. It is just simplified to include negative g. So I still recommend to use this equation, and just throughout your calculation, you can use the value of negative 9.81. Displacement can be used using a function of time. So we have here the equation discussed on previous lectures. So we can use this equation to use for the to solve for the position of the particle and the projectile along its y-axis. So substituting the value g in this equation yields to this equation. Again, this equation is equally correct. We just simply substitute AC with negative g. You can see this in some books, but this is also correct. I recommend you to use this one instead of this one. Just make sure that if you place the value of the gravity, it should be taken as negative 9.82. So again, that 9.81 is a unit of meters per second squared. If you want to use the English units or the US customary units, we have it as 32.2 feet per second squared. So the velocity and position can be both expressed in an equation. We call the position as a function of position. This is also an equation used in the rectilinear kinematics. We can use this one if you want to solve for velocity. So again, we have three equations for the rectilinear kinematics that we can use to assess the geometric aspects of motion. Since we can treat the vertical motion of a projectile like the rectilinear kinematics. So substituting G in this equation, we have this one. Again, you can still use this equation. Just simply substitute negative 9.81. The rookie error here is that if you use this equation and you substitute the negative 9.81 in G, it will give you a positive value on this one. So, which is the common error of students, of some of the learners. So, I still recommend using this equation, since if you will substitute the negative value, it will retain its correct sign. So, for a horizontal motion, we use this one. And for the vertical motion, we use these three equations. Again, for the horizontal motion, we just use the definition of velocity. But for the vertical motion, since it is influenced by acceleration due to gravity, we will use the three equations of rectilinear kinematics, which was discussed on previous lectures. So for the procedure of analysis, the first thing we do, we establish a fixed x and y coordinate axis and sketch the trajectory of the particle. Between any 2 points on the path specify the given problem data and identify the three unknowns. In all cases, the acceleration of gravity acts downward and it is equal to 9.81 meters per second squared or 32.2 feet per second squared. The particle's initial and final velocities should be represented in terms of their x and y components, like we do in the general curvilinear motion analysis. Remember that positive and negative position, velocity, and acceleration components always act in accordance with their associated coordinate directions. Let's have a sample problem here. An object was fired up from ground with a velocity equal to 20 meters per second, with a direction of 60 degrees measured from the positive horizontal axis as shown in the figure. We are to determine the x-component velocity at the highest point of the projectile. So to do that, our first step is to draw the projectile according to the given. So we have here the trajectory drawn from point A to point C, where B is the point of the maximum height attained by the particle. So we represent the velocity in its rectangular coordinates. So we have the x component, VAX. VAX means this is the velocity at point A, and it is the x component of VA. Similarly, we do the same representation of velocity along y-axis. So VAY represents the velocity at point A along y-axis. So we establish the x and y-axis and specify points along the projectile where analysis is required. So it is recommended or a must to establish the point B in this case because we are asked on the highest point of the projectile. So we assume that point B is here. So you can draw this in scale or not, but the most important thing is you draw the trajectory of the projectile and you select the apex at this point, and this will be the maximum height, and then label it as point B. So you can label it any way you want, but for me, I think it's convenient to use point B. So from point A to point B, the particle will travel with an initial upward or positive velocity, and then eventually it will have a 0y component velocity. So I established that point A is the origin where x is equal to 0 and y is equal to 0 in terms of its position. So the x component velocity at the highest point of the projectile is also equal to the x component at point A. We have this equation. So we can easily identify the answer at point A because of the principle that the x component velocity is equal throughout the plane. So if we get VAX, we can already have the x component velocity at point. So the velocity along x-axis is constant. We can solve VAX using trigonometry. So the VAX is simply the x component of the initial velocity. So we have VA cosine 60, and we replace VA with its magnitude. So VAX is equals to 10 meters per second. And this is also the value of VBX, or the x component velocity at point B. Second question is the time it takes for the object to reach a maximum height. So since we are talking about the velocity movement along y-axis, we will be using the three equations of kinematics that we have discussed earlier. So recall that the maximum height VBY is equals to 0. It's because we reached the maximum height of the projectile, wherein a positive value of y component gradually decreases until it reaches a 0 value, and then it will start to gain a negative value of y component velocity. So this point B, where the y component velocity is 0, is taken as the maximum height attained by the particle. So it is recommended to use this equation, because this equation gives you the initial value of y component and the final value of the velocity. If we're analyzing from point A to point B, again, we can use velocity at point A, velocity at point B. They are both known. And from our discussion, since point B is the maximum height attained by the particle in the flight of the projectile, Vy is taken as 0, and V sub 0y is taken as the y component at the initial point. So rewriting this equation, I think it's better to rewrite your equation so that you can easily identify which values of velocities are you going to substitute. So the initial value, Vay, and the final value of velocity is Vby. Again, Vby is taken equal to 0, and Vay is simply the y component of Va. And then don't forget to incorporate the value of 9.81 in your equation. Again, I've used the negative GT, but if you will use plus 80, it's okay. And I think it's way better, but it will still yield the same answer. You just have to be cautious when you substitute the value of gravity. So I can solve now the time of travel from point A to B. So time from A to B is 1.77 seconds. So we have now the second question. So for the third question, the maximum height reached by the object is at point B. Third question, the maximum height reached. So we are to solve for the position of point B in terms of y-axis, or the height. So again, we're talking about y-axis or vertical motion. So we will use the three equations of kinematics. So I will use this equation, and I will also use this equation. By the way, you can actually solve the position of point B using equation 2 directly. So using equation 2 and keeping in mind that ya is equals to 0, because we established that point A is our reference, so we can solve now for the position of B. So we substitute using equation 2, 0 squared is equals to VA as the initial velocity minus 2 times 9.81, YB minus 0. And then you can solve for YB, that is 15.29 meters. And this position of B, again, is relative from point A. If point A is on the ground and you are asked what's the maximum height attained by the particle, you can say that it is 15.29 meters above the ground. But it's more organized or proper to show it in terms of position. So next, the value of S when the object hits the level ground. So we're talking about the distance traveled, or the horizontal displacement of point A to point C. So we're talking about the horizontal axis, so this means we're only using the definition of velocity because we have constant velocity, constant x component velocity throughout the flight. So if the time of travel from A to B is 1.7 to 7 seconds, then the time of travel from B to C is also 1.7 to 7 seconds. So we can say that the total time of flight is equal to 3.54 seconds. Then we can use that using the definition of velocity. So the velocity is equals to change in position over the time elapsed. Using the time elapsed of 3.54 seconds, we can solve for the displacement. So the x component velocity is constant, and xa is the coordinate of point A, which is 0. So we can see here that x component dx is here, xc minus 0 divided by 3.54, and then you can solve now. xc is equals to 35.4. Now, the next question or the next requirement will be the time it takes for the object to reach back to the ground. So we have already solved this one while we are doing the requirement B or this answer. So we have determined the time to be 3.54 seconds. Now lastly, we are asked on the magnitude of velocity and position of the object after 2.5 seconds. So after 1.7 seconds, object is here. But after 3.54 seconds, it's at point C. So somewhere in between B and C, is the time of 2.5 seconds. So we are asked on the magnitude of velocity. Thankfully, we can easily identify the x component of the velocity because it is constant throughout the flight. What we are now required to determine first is the y component after 2.5 seconds, or the y component velocity after 2.5 seconds. So let's do that. X component velocity again remains the same at 10 meters per second. Meanwhile, the y component velocity, we can use this equation. So we're setting VA as the initial point and V2.5 as the second point in this projectile. So again, we substitute the y component velocity minus 9.81 times time. You can get the velocity that is equal to negative 7.2 meters per second. If it's correct, as you can see, if this point is after point B, then it should have a negative velocity. So it is correct. So the magnitude of velocity can be determined using the Pythagorean identity, where the velocity after 2.5 seconds is equals to x component squared plus y component squared, and then you get the square root. So solving for that, we have the velocity after 2.5 seconds equals to 12.32 meters per second. Now, the position in x coordinate, the definition of velocity after 2.5 seconds, what is the position? We'll use this one. We know the position at A, we know the time, we know the x component velocity. So the x position after 2.5 seconds is 25 meters. And if we're talking about the y component or the y-axis, the vertical motion, we'll use this equation because it will tell you now the position after 2.5 seconds, because you know the position at point A, the velocity, y component velocity at point A, time, and the value of gravity. So we substitute the values. We have 0 plus the y component of velocity at point A, the time is 2.5, the gravity is 9.81, and the time again is 2.5. So we have y 2.5 is equals to 12.64 millimeter. So this is actually now your position along x after 2.5 seconds, and this is your position along y after 2.5 seconds. Let's have another problem. In this case, a shaft slides off the ramp with a horizontal velocity of 12 meters per second. If the height of the ramp is 6 meters from the floor, determine the time needed for the sack to strike the floor and the range R where the sack begins to pile. So let us establish position of point A. So the first thing we do is we draw the projectile. So from point A to point B. So since the sack slides off the ramp, that means this is the highest point of the projectile. It has an initial velocity of 12 meters per second to the right. So this 12 meters per second will be constant throughout the flight. The variable will be the y component velocity. This time, the y component velocity is 0, but because of the acceleration due to gravity that is negative, it will add and add and add a negative value of velocity to point A or to the sack. Now, the position at point A is 0. The position at the y position at point A is also 0. So obviously, the position at point B is at positive x and negative y. Again, positions are relative. So if we establish an origin at point A, then everything will be measured from point A, and it follows the sign convention on a Cartesian plane. So, and we are asked to determine the time. So since the initial velocity is directed to the right, we have VAY is equals to 0. We can determine the time it takes the rise to reach the ground by using this equation. We are using this equation since we know the position at point B, position at A, and the initial velocity, y component velocity at A, and we can solve now the time it takes from point A to point B. Let's substitute the values. So we have the position of point B relative to A, that's negative 6, equals to the position of A is 0, plus 0 times time minus 1 half, 9.81 TAB squared. Now, you can solve for that. So TAB is equals to 1.11 seconds. And to determine the value of the range, we will just use the definition of velocity. This is easier because we have a constant value of velocity along x-axis. The position of point B will define your range measured from point A. So obviously, it's an equation, xa is equals to 0, and TAB is also the time required from point A to point B, which was determined previously. So we have Vx equals to 12 meters per second. And then xb now is equals to 13.32 meters. And that's also the range. Now another problem, this is a bit more complicated. The track for this racing event was designed so that riders jump off the slope at 30 degrees from a height of 1 meter. During a race, it was observed that the rider shown remained in midair for 1.5 seconds. Determine the speed at which he was traveling off the ramp, the horizontal distance he traveled before striking the ground, and the maximum height he attains. We are to neglect the size of the bike and the rider. So, the first thing we do, we establish point A, which is our reference. So, which means our position will be measured at point A, which is 0, 0. So, YA is 0, and B, this is given, is negative 1. So, it is stated that the rider is airborne for 1.5 seconds. So, we can have this equation. It's practical to use this equation because the position of points A and B are given. The time it takes to travel from point A to B is given. Then we can solve now for the initial velocity of the particle or the object, which is the racer. So let's substitute that. YB is equals to negative 1. The position of A is 0. VAY is the y component, so that is VA sine 30. Time it takes to travel from point A to point B is the mid-air time, that is 1.5, minus 1 half 9.81 times 1.5. So the initial velocity is taken at 13.38 meters per second. We have here the initial velocity. Next, horizontal distance it travels before striking the ground, and that is the range of the projectile. Since we know the initial velocity and we can solve for the x component velocity. We will just use the definition of velocity itself. So x component velocity is constant throughout the flight. So we can easily get the x component here of PA. We know the position of point A, and we know the time of travel. So we can solve for xb, and then eventually xb will tell you the range of the projectile. So VA cosine 30 is equals to XB minus XA over KAB. Substitute the values, and then we get XB is equals to 17.38 meters. Now, to determine the maximum height of the rider during mid-air, let us use the formula. Now, it is important actually for you to draw the the projectile, because it will give you an idea on how will it travel, and that we can identify or make a diagram showing for what point we can analyze next. So we have here point C as the highest point during the projectile, and we can use this equation. There are actually three equations that you can use, like what I said, on analyzing the vertical motion. So you just simply select which of the equations will allow you to solve for the unknown. In this case, we are solving for the position at point C. So we know the initial velocity, and we know the final velocity will be 0 if we're analyzing from point A to point C. So this equation is very helpful because it will give you only one unknown, that is the position of point C. Now let's substitute the values. VCY is 0 at maximum height, replacing known values. We can solve for YC. We substitute the values, that is 0, and this is the initial y component velocity at point A, minus 2 times 9.81, YC minus 0. And then there you have YC. But since we are asked on the maximum height measured from the ground, and YC is measured from point A, so we'll need to add +1 since A is 1 meter above the ground. So if we're asked on the height measured from the ground, we need to add this one. If we're only asked on the position of the rider at maximum height, then we'll just have 2.28. This is our topic for projectile motion. I hope that you have learned from this lecture. Thank you very much.